Chapter 11, Design of Beams and Shafts, example number 1. This example, we are talking about the section modulus. So we do have modulus of elasticity. We show that by E, and we have another definition that's a section modulus, and it just goes by two main categories when the section is in elastic domain and the other one is a plastic section modulus. We show the first one by capital S and the latter one with the other one with the capital Z. So Z is plastic section modulus and S capital is plastic section modulus. Let's go with the elastic domain. Sigma maximum due to bending is m bending moment times distance mc over I moment inertia. And if we just define I over c by a parameter like capital S and define that as elastic section modulus, we can rewrite the bending stress equation. Sigma maximum is capital M over capital S. And the way one effective way to increase the stresses in a structure is just increasing the section modulus. By increasing S, denominators is increasing, then maximum stress is decreasing. So just assume we have two solid rectangular cross section with the identical area. Both of them are equal in terms of their area, 24 inches squared. The first one has a width of 4 inch times 6 inches, and the other one, section B, has the height of H and B of 3 inches. So if you want to know which one is a better section, so if you just calculate the section modulus, that's a moment of inertia over C, which is the distance to the centroid, for example, this problem, that's 112 base cube height over H over, which is a half of height, that's 16 BH squared. And it just says if their area is the same, S or modulus of section is 1/6 of A times H. It just says with the same amount of area, the section which has higher height, bigger height, it just goes by a higher modulus, section modulus, which increases the denominator and decreases the stresses drastically. So definitely section B is a better than one in terms of stress analysis. Likewise, if we just rearrange this equation, my is in elastic domain, that's 1 I over c times sigma, and m is s times sigma, my, it just goes by s capital times sigma y. That's for elastic section modulus. And also we do have a definition for plastic section modulus. If you are interested in that one, I will provide you with the link at the end of this video. That's M plastic. Sometimes you want to use the maximum capacity of the section. That's A capital over 2 times Z. And we call this parameter Z capital times sigma. So that goes by Z capital, and that's plastic section modulus. And this small z here is the distance from tensile section centroid to compression centroid. Likewise, M plastic is a plastic section modulus times sigma y. So let's put it into an example, like if a beam, two simple support beam A and RA and RB, handling two concentrated load at different distances like 40 kips and 2 20 kilopounds. So if we do know that all how it's a steel beam and sigma not this is how allow the sigma allow. So that's a sigma acceptable and tau acceptable are respectively 24 ksi and 14 ksi. We want to select an appropriate W shape section which will carry the loading shown here. So for this kind of problem, we are looking for section modulus. And that's from the formula, that's M maximum or sigma alone. So we definitely need to draw the shear moment diagram and get the maximum shear if it's here, 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 here. Priorities, we need to calculate M maximum, then go for calculation of section modulus. So if we want to draw the shear and moment diagram, first of all, summation of moment above, for example, A goes 0, summation of moment above point A goes 0, and that gives us a negative 40 times a distance 6 inches plus RB times 12, that's RB times 12 minus 20 times 18, that's a 6 times 3, that's 18, and it just that's the all of the forces. It just gives us RB 50 kilopounds, and then summation of forces in y direction should go 0, 60 minus 50 give us R a 10 kilopounds. Then for drawing the shear and moment diagram, as soon as we know the reaction, so it just comes by the amount of RA, which is 10, no nothing, to when you move to the right, and all of a sudden 40 drop down, it just keeps us to a positive 10 minus 40. This is meant minus 30. No nothing from this part. All of a sudden a reaction of 40 takes off all high. A negative 3 plus 50, that's a 20. No nothing here until downward force. It just brings us back to the x-axis. And if we want to draw the moment, the area under shear, area under this rectangle, just translate to this triangle here, and is the maximum, the value of here. It just a area. This area is the here. It just there is no moment at the free end and at the beginning, so those are 0. So if we want to show the numeric value, that's a RA 10 kilopounds, negative 30, positive 20, and likewise this is 60 because a 10 times 6, that's a 60, and then the area under here, that's a negative 180 minus positive, that gives us a negative 1 to 120. So for bending the stress, this is our maximum M. As you can see in the figure for M graph, that's the maximum amount of F. Forget about the negative or positive, just the numeric value. Bending moment is S equal to maximum M, which you can directly replace 120 M maximum sigma alpha is provided. Problem statement 24. If you just do the math, it just gives you 120 kilopound feet pound feet. Then you convert it to inch over 224 ksi. It just makes give us a modules of section of 60 inch cube. As soon as we have our section modules, we can jump to the table of y flank section, because we are working to find the most appropriate W-shaped section FPS unit. So just look at the section which are close to 60 or more. So for example, the first one is W18 times 40, which gives us a section modulus in x direction of 68.4. That's acceptable. We can something like 10 numeric value higher, but it's still in a good shape. Other one is W16 times 40. It's a 72. A bit too high. W14 times 40. 3, that's a S of 62.7. That's a good one. And also can have W12 times 50, 64.7. W10 times 45. It just gives us a 10 times 45, a 54. The other one is W8 times 67, that's 60. So the problem is talking about the most appropriate bonds. So by the term most or an appropriate section means we want the lightest section. We don't have any weight on this table, so you just need to know W. Weight is gamma times V. Gamma remains the same for the same material. So if we are working with a steel, gamma cancel out for all the material. V is B or A times, for example, Z, the other dimension to the. So if we just consider this one is equal to unit, because that's for unit of length. So that says W is gamma times the area times 1. So if that's the case, it means if as soon as I know what A is, I can work with my section. So let's take a look at the area of each section. So this one is 14.7. The smallest area is my answer. This is 15.8. This is 19.7, which is the minimum is 14 so far. Let's see here. This is 11.8. This is 13. This is 12. So again, if weight is gamma times A times H of 1, the smallest the area gives us the lightest section. So as you can see here, W18 times 14, the 40, it gives us the smallest area, and that's also the smallest or lightest weight white flat shape. So if we just move to the white flat section selection, you can easily see we take out these sections from our tables. These 6 sections, each of them gives us their own modulus of section, and you see this one was the lightest one. So let's go by W18 times white flange of 18 times 40 with modulus of section of 16.4 inch cube. This is our selection. So we just select this one because that's the lightest section. As soon as we have all section. And also the easier approach for W wide flat shapes are distinguished. There is this easier approach to not go through the table for the area and for the weight, so they are designated by their depths and weight per unit length. So that's a cool meaning. So it just says if I have a wide flat shape, it just goes by two number, 18 times 46, for example. So it just gives me the first number gives me depth or height of section. That's a entire depth of section. That's 80 inches, the first number. And the second number, it just gives me a weight per unit of length. That's a 46 pound per feet weight for weight. So if we just take the second, the unit of what we are working with of the section, it just gives us the weight. So just let's see here, this is 45 pound per feet, 45, 43. So you can easily see the smallest is this one, and it just increasing, increasing. On this one, it just 45 is bigger, but 40 is the smallest or lightest section, which we already calculated from the area. So as soon as we have that, and just be careful if you have your wide flange section like this. For example, if this is W18 times 46, it has entire height of the section is equal to 18 inches from the top of the top flange to the bottom of the lower one, and this is 6 inch. That's the of flange, and it just gives depth or height of section is 18. Weight per unit length of weight is 46 pound per feet. Just be careful. This is not the real depth. Real depth is something like a bit different than the one which is provided in the number, maybe by 2 digits, something like a small variation of that. So you can easily go with this number and take this number like the weight of the light a W-shaped section and solve your problem. So the next step, as soon as we have our section, as soon as you have your section like this section, so we need to, for W times 18 times 40, which is our section, we need to go to Sx is equal to what? Is equal to what? And then Tw is equal to what? I need to modify this. So depth is 17.9 for 18 times 40, and then the TW is, as you can see here, is 3 inch cubed. I hope S is correct. Let's see how that goes. Then we need to go for the shear check, and for checking the shear, if you remember tau maximum, some codes allow us to use a approximation of V maximum over TW times C rather than go by a far more time consuming equation of tau max is, which is EV times cubed over IT. Some code just allows to go with this approach, so it makes the problem far easier. We already know what the maximum is, so that's a negative 30. So over TW times BD just comes from here. And if you do so, it just gives us a shear maximum equal to 5.32 KSI, and that's definitely smaller than all allowable, which is 14.5 KSI, so we can simply use W18 times 40, and that's solve more problem. That's all problem. I will solve more problem in next videos. Thank you.